Bienvenidos todos a la primera sesión del Coloquio DIV. So now I will change to English. Welcome everybody. So this is the first time that we are doing this colloquium. The main idea is that we are going to do this at the end of each month. And the main objective is that we are learning together mathematics. So we can enjoy about this. And now I will present, Gabriel will present the first speaker.
Okay, it's a pleasure to me. We are so happy of receiving here Filomena Pacella. She's a full professor at the University of La Sapienza, and for more than 30 years. Yes, also been working also in France, in United States, and she's one of the most important and influential people in PDEs nowadays. So we are very happy of receiving you here. Please.
Okay, Gabrielle, thanks. So thanks to Gabrielle, thanks to everybody for the invitation. I'm very, very happy to be in Chile. It's a beautiful country. I mean, with very interesting mathematicians in many areas. And so people are very kind. The country is beautiful. So what I want more. Okay, so this is a kind of a colloquium. So I understand that not people are specialists in something in particular in PDEs and so on. So I will keep my talk quite general, and in particular, the first part will be very general, and then I will try to give ideas of what are the recent developments in these two subjects. Okay, so let me first start the page if I can. Okay, so as you see, the first line is a subtitle of my talk. So what I will speak is concerns this question of shape optimization theory and symmetry. What does it mean? What does it mean usually shape optimization? This is a word that many of you can have heard. So the idea is this: you have a set, a family. Okay, this is not working. It's working. This one, I think. So you have, let's say, a family A of domains, subset in Rn, for examples. So this is a family of something. And in this family, you define some property. Property, or maybe you define some functions in this family A, defined for every element in this family A. And you may ask, what are the elements of the family which satisfy this property? Often, for example, the property can be given in terms of functional, which is defined on this family, and which associate to every element of this family a real number, for example, and you want to minimize this. So you may ask, what are the elements which minimize this functional, or what are the elements of this family which enjoy this particular property you are studying? Okay, so this will be the optimal set, the optimal elements for your problem. Okay, so often, and I will describe two problems of this type, often you may see, or you may guess, that this optimality is obtained using symmetric domains. Okay, this for several reasons. In application, in nature, and so on. Okay, so what I will show is that this, what I will present, that this is historically true for some questions which are classical questions in geometry and data analysis, but we can also have a break of symmetry sometimes. And so I will try to explain these two sides of the problem. Okay, so let me start with two classical problems in geometry and in analysis that you will see they are more related with respect to what they look at the first glance. So the first one is a classical problem, which dates back to centuries ago. So you have a closed surface. A closed surface is a surface. When I say the word surface, I mean one codimension, one manifolds, which usually are smooth. Okay. So closed for me means compact and without boundary. So you may ask, what are the closed surfaces which have constant mean curvature? So this is a very classic and ancient question, which was completely solved by Alexandrov. In 1962, I'm mentioning here the reference to the English version of his paper, but in fact, he solved this question in 1956. And he was the first one to solve completely this question, in the sense that he proved that the only surface, closed surface, which have constant mean curvature are spheres. So it's a symmetry result. Let me tell you that 100 years before, there had been a result by a mathematician called Jellett, who proved the same result, but just for star-shaped domains about the point, around the point. So it took 100 years to pass from star-shaped domains to star-shaped surfaces to close to every kind of closed regular surface. But what was very interesting about the proof that Alexandrov made up, had the intuition of using, it was that the proof is entirely based on PDEs. In particular, it's entirely based on the maximum principle. In fact, he introduced in mathematics this method, which since then is called the method of moving planes, which is a method to get symmetry using maximum principle for PDEs. So why the PDEs enter? Because if you have a regular surface locally in the neighborhood of a point, you can describe it as a graph of something, of a function. And then if you impose that the curvature is constant, then this function satisfies a certain PDE. And this is the way the PDE enter in, let's say, in this problem in geometry. Okay, so this is a beautiful result, classical result in geometry. And then let me shift to a second problem. So let me just tell you that in terms of optimization, this tells you that if you take the class of all closed surfaces, then the optimal surface is the one which have constant mean curvature is essentially just one, it's just the sphere. Okay, then let me shift to a second classical problem, which is an overdetermined problem. It's a very simple Poisson equation, minus delta U equal 1, in a bounded domain omega in Rn, and you take it smooth. And you assume the Dirichlet boundary condition, okay? So if you just take these two things, the equation plus the Dirichlet condition, then in every bounded domain with a certain regularity, you have a classical solution. But then you impose an extra condition that the normal derivative is constant on the boundary. And you may ask whether there are domains for which this problem, which now becomes overdetermined, has a solution. So in principle, there could be no domains with this property. If you think that omega is a ball and you take the radial solution, which at that point is the only solution of this problem, of course, this satisfies this property. So you may ask whether the ball is the only domains with this property, and this is in fact true, and it was proved by J.Serrin in 1971. So if there exists a classical solution of this problem, then U is radial with respect to a point, and then at that point, the solution is necessarily this one. Okay, so why I am mentioning this problem after the other one? Because the proof that Serrin gave is very similar to the proof of Alexandrov for the constant mean curvature surfaces. In fact, he used the moving plane method adapted with, let's say with a strong intuition to a problem in PDE. So using again strongly the maximum principle. And actually he proved the same result not only for the Poisson equation minus delta U equal 1, but also for general semilinear equation of the type minus delta U equal f of U. So it's remarkable that the proof was very similar, and you may ask whether there is a connection between this problem. I will try to to enlighten a bit the connection between this problem. Let me also tell you that at the same time when Serrin proved this result, Weinberger in the same year, 1971, gave another proof of the same result, but only for the Poisson equation, which did not use the moving plane method, but used the integral identities. And again, for the constant mean curvature surfaces, in 1997, so many years later, Rayleigh gave another proof of the Alexandrov result, which is essentially related to Weinberger proof. And it's very much where you can see more let's say, the relation with this overdetermined problem, because what Rayleigh did, he was considering a closed surfaces in Rn, and he considered, so a closed surface can be considered as the boundary of a set omega in Rn. And this set omega, he was considering exactly the problem, the Serrin problem, let's say the Laplace equation, the Poisson equation. And then what he showed is that an interesting fact that if the boundary of omega has a constant mean curvature, then using some integral identity, he proved that the normal derivative of the solution of this problem in omega is in fact has in fact a normal derivative which is constant. Then if you already knew the result of Serrin, you would deduce it from this result. So you can see that in a sense the constant mean curvature problem was implying the overdetermined problem. So there is a relation between the two things, the two problems. But they are not equivalent. You cannot say that every time. You cannot say that every time that you have a constant mean curvature, the normal derivative is constant, or especially you cannot say it vice versa, especially in the case of unbounded domains. But for this problem in bounded domains, with Dirichlet boundary condition, it was true. Okay, so now let me, again, in terms of the optimality that I was telling you before, the Serrin result and this other equivalent result tells you that if you look at the class of domain where you can have a solution of this overdetermined problem, again, you have full symmetry. So the only domain are spherically symmetric are the ball or the spheres. Okay, so let me give you now the relation between these two problems, in particular the constant mean curvature problem, with another classical problem, which is the isoperimetric problem. So the isoperimetric problem can be seen as, let's say, the first shape optimization problem. What is the isoperimetric problem? You have a region in Rn with a certain fixed measure, okay? And you may ask, among all domains with a fixed measure, what is the domain which has the smallest measure of the boundary? So this is the classical Dido problem, the classical isoperimetric problem. And in a full generality, this was solved by De Giorgi in 1956, I believe, with this famous isoperimetric inequality. And the contributor of De Giorgi was very important because he was considering not particularly regular domains. He was considering measurable domains in Rn with finite measure, and he was considering, he was defining, in fact, he was the person who defined a kind of measuring the boundary of the domain, even when the domain is not so smooth. But okay, I don't want to enter into this, but if you are not familiar with what is called the Giorgi perimeter, you can think about the n-1 dimensional Hausdorff measure. Okay, so the classical isoperimetric inequality is this one. So what does it tell you? It tells you that the perimeter is always greater for every set measurable. The perimeter is always greater or equal than a certain constant, which depends only on the dimension where Cn is the measured unit ball, times the volume of the set with a certain power. And the important fact is that equality holds if and only if the set E is a ball. So in other words, the balls are the only set which minimize the perimeter where you have, once you have fixed the volume. So this was proved by the George in 1958. Okay, so this is the first, let's say, I would say one of the first problems which were denominated with the name the optimal shape optimization problem. So the optimal shape, if you want to minimize the perimeter, is given by the shape of the ball. Okay, so what is the relation between the isoperimetric inequality and the constant mean curvature problem? The relation is the following one. If you take, let's think about a smooth domain, you could consider the function which associate to every domain omega the perimeter of its boundary. Okay, think about the n-1 dimensional Hausdorff measure. So this is a function. Of course, it's a function of domains. Okay, but even for function domains, there is a tool in mathematics which is called shape derivatives, domain derivatives, which allows you to consider to differentiate this function with respect to the domain, let's say, where with respect to variation of the domains, which are obtained through smooth deformation. So if you do this operation, then many people here work in variational setting. Then you may ask, so once you have defined the derivative, you may ask what are the critical points of this functional with the constraint that the volume is fixed. This is, I mean, you understand this is an obvious constraint that you have to put, otherwise there is no reason to minimize the perimeter if you don't fix the volume, okay? So you may ask, what are the critical points? And it can be proved, I mean, also this is quite classical, that if you take the domains omega, which are the critical points of the perimeter functional with respect to variations of the domain, which leave the measure fixed, then these are domains whose boundary has a constant mean curvature. Okay, so the constant mean curvature surfaces are the boundaries or the critical points of the perimeters. So the Alexandrov theorems, in a sense, is more general than the isoperimetric inequality, because it tells you that all smooth stationary domains, critical points, critical domains of the perimeter functional are in fact the balls. So not only the minimizers, but all critical points are just the balls. The balls or the spheres is the same thing. Okay, and then you may understand that the isoperimetric inequality is the basis for symmetrization results. For example, for the theory of symmetrization developed by Schwarz. And then this gives you symmetry for minimizer of a lot of variational problems. It allows you to find the best constant in Sobolev inequalities and so on. Okay, so this is let's say the classical stuff that I wanted to recall in order to introduce now a new problem which has attracted some attention in the last years, let's say. So the question is what I have written here. So these three things that I have mentioned, isoperimetric inequality, the constant mean curvature surfaces problem, the overdetermined problem, you can see all as a characterization of a ball. Each one of them characterize the ball as being the only domain which has a certain property. What I would like to see now, to describe, is whether it's possible to have the same characterization for domains inside the cone, which are radially symmetric. So I will, okay, let me just shift to this question. So what is a cone in Rn? So a cone in Rn is a domain which is spanned by a smooth, I'm taking a smooth cone, smooth domains on the sphere. Okay, so, okay, maybe there is no need to have another picture. So it's something like this. So you have a cone, and I'm considering the domains omega which are inside the cone. Okay, and in particular, among this domain, there are this one, which I call a spherical sector, which are given by the intersection of a ball with the cone. Okay, but you can have many different kinds of sets. And so I'm considering my attention will be on the boundary of a set omega inside the cone, which is the one which is inside the cone, so the red part. So this red part is usually called the relative boundary. So it's the part of the boundary which is inside the cone. And then the other part is the one which lies on the cone. The cone is fixed. So you can consider this as a free boundary. And this is a fixed, the part which lies on the cone is a fixed boundary. And I'm particularly interested in the domains for which this part of the boundary which is on the boundary of the cone has a positive n-1 dimensional Hausdorff measure. Otherwise, the domains just become any domain inside the cone, which then the cone will not play a role. Okay, so let me just tell you that I mean, what I've described before is are problems where the domains omega are free to move in the whole Rn. What I'm describing now is a setting where the domains are not free to move in the whole Rn, but just inside the cone. Why the cone? I will try to explain later the interest for the cone in particular. But in general, this is part of this problem, which are called, I don't know, I mean, relative problems, let's say, or free boundary problem, or capillarity problem. So these are problems where you have a certain region in Rn, and for some reason, whatever you are studying happens in that region. This is, for example, related when you want to study the spreading of a species in the population dynamics, for example. You have a certain region, so everything happens there. So there is no reason to go outside of this region, okay? So this is, and the region in my case is a cone, but in principle, you could consider other regions. Okay, so the interest for the cone, apart from something that I will tell you later, is because in the cone, you can define a radial domain, which is the spherical sector, okay? So then you may ask whether, with respect to the problem that I mentioned you before, isoperimetric problem, constant mean curvature surfaces problem, overdetermined problem that should be adapted in this context. What you would like to know is whether the spherical sector play the same role as the ball in Rn. Okay, is it true that the only minimizer for an isoperimetric inequality are the spherical sector? Is it true that the solution of the overdetermined problem are the spherical sector, and so on? So let me introduce this problem, and let me tell you what is known and what is similar to the case of the classical case and what is different. Okay, so let me start with the isoperimetric inequality. So what is now the problem when I am considering domains which are restricted in a cone? So I am considering a cone. I'm taking any particular domain, any domain omega, and this gamma is the relative boundary. So it's the part of the boundary which is inside the cone. So I'm fixing the volume of omega. And I'm posing the following question. So among all domains inside the cone, for which have a fixed measure, what is the domain, or what are the domains which minimize the relative boundary? So just this part of the boundary. So this is the part of the boundary I'm interested in. So is it true that is the spherical sector? Is it true that the best domain is this one? So the one which has the smallest relative boundary? Okay, so let me tell you what is the answer. in one case, so this is a relative isoperimetric inequality. So what is this object here? I'll call it relative perimeter. So this means it's the measure of the boundary that I'm calling here gamma. So it's the measure of the part of the boundary which is inside the cone. So this is called the relative perimeter. So you see, you will have an isoperimetric inequality which is similar to the one that I had before, where this time this absolute constant omega n is nothing else than the measure of the unit spherical sector. So, and it tells you that equality holds if and only if E is a spherical sector centered at the origin, which is the vertex of the cone. But this is true if the cone is convex. So this relative isoperimetric inequality tells you that the best domains are the spherical sectors. So the only measurable set which minimize the perimeter once you fix the volume are the spherical sector centered at the vertex of the cone. But this is true if the cone is convex. Okay, so what I would like to discuss now is the role of the convexity. But first of all, let me give a bit of history of this relative isoperimetric inequality. This was proved in the first time in 1990 by Pierre-Louis Lyons and myself using kind of inequality for sets. Let me tell you immediately that the proof of the Giorgi was using the symmetry of the sphere or the ball in order to produce his result. Here there is no symmetry. I mean, the domains are, in a sense, are radially symmetric, these domains here, but the cone is any cone. I mean, you do not have any symmetry. So you cannot think, for example, of using moving plane methods in these cones and so on. So we used a kind of Brun-Minkowski inequality, which is an inequality among sets. Then the same theorem was proved 15 years later by Ritoré and Rosales, and they used another method which was based on calculus of variation. And then it was again proved in 2013 by Figalli and Indrei, and they proved it using this modern technique of optimal transport. And then it was proved again by Gabrero, Soton, and Serra in 2016 using PDEs, an associated Nomian problem. So all different proofs and all require the convexity of the cone. The Figalli-Indrei's proof gives also an additional stability result. This isoperimetric inequality does not hold in general in non-convex cones, and we had a counterexample in our paper, quite easy to construct. But it holds if you perturb a bit the convexity of the cone. So this was some kind of conjecture by the Giorgi, and it was proved recently by Bayer and Figalli. Okay, so this is for the analogous of the isoperimetric inequality. Now, if I told you before that if you take the perimeter, the Giorgi perimeter, if you take the functional of the perimeter, and instead of studying the minimizer, you study the critical points, then you end up with the domains whose boundary has a constant mean curvature. The same characterization holds in this context. If you consider the relative perimeter function, so the one which measures only the part of the boundary which is inside the cone, and if we take derivative of this function that you can do in the sense of domain derivative, take the formations of your domains, and you study its stationary points or critical points, then in fact these are constant mean curvature surfaces which intersect the cone orthogonally. Like, for example, in the case of the spherical cup, the spherical sector. The cone, they are orthogonal to the, they are orthogonal. They satisfy this. This is a constraint which comes because you are deforming your domain with respect to variation which leave the cone invariant. So this is the condition that comes from this reason. Okay, then you may ask whether an analogous of the Alexandrov results holds. assume that you have the constant mean curvature surfaces which intersect the cone orthogonally. Can you say that the only ones are spherical cup? And this was proved by Cho and Park in 2011, and then by Giulio Tralli and myself later in a more general setting, with a more general boundary condition in a sense. But anyway, the result is that if the cone is convex, so again, the convexity of the cone plays a role, then the only constant mean curvature surfaces which intersect the cone orthogonally are in fact pieces of a sphere. Are either spheres centered at the center of the cone, at the vertex of the cone, or they may be also half spheres, like this, for example, if the cone has a flat portion, that's obvious. But so if the cone does not have a flat portion, then the only possible constant mean curvature surfaces which intersect the cone orthogonally are the spherical cup. Okay, so let us then shift to, there is an analogy again with the Alexandrov result. So let us shift to the overdetermined problem. Now, the right overdetermined problem that you have to consider in a domain omega inside the cone is not at all, it's not anymore just a Dirichlet problem, but the right problem is this one. Okay, you have the same Poisson equation, then you impose u equals 0 on the relative boundary inside the cone, and then the normal derivative 0 on the boundary. And this is reasonable because you don't want to leave the cone. So this is a natural condition it arises because you are inside the cone. So you may see this as a Dirichlet problem on the relative boundary. Okay. Then the question is this: assume that you impose an extra boundary condition just on the Dirichlet part of the boundary, so the one which is the relative boundary. Then is it true that the only domain which satisfies this overdetermined problem is the spherical sector, and then the only solution is the radial solution? Okay, the answer is again yes, if the cone is convex. So this was proved with Giulio Tralli. If the cone is convex and U is a classical solution of this overdetermined problem, then necessarily omega is a spherical sector or a half ball if you have a flat part of the boundary, which is the trivial case. So if you do not have a flat part of the boundary, then the only possibility is that you have this one. Okay. What is the proof? The proof that we used is by integral identities. We cannot use the proof of moving plane methods because, as I told you, there is no way you can move the plane here. And you should move the plane starting from the Dirichlet part of the boundary, but you immediately go out of the domain. So there is no way you can use moving plane method. Okay, so then the question I want to address, and so, I mean, just to give an idea, that what is interesting is now the case when the cone is non-convex. Results may not be true. When they are not true, for which non-convex cone they are not true, and if there is a break symmetry. So this is interesting because it tells you that in non-convex cone, if we succeed to understand this, at least partially, then you may produce optimal shapes, optimal constant mean curvature surfaces, which are not spherically symmetric. And then it will be very interesting to understand the shape of these domains. Okay, so these are better than the spherical cones, the spherical sectors. Okay, I will describe the result a bit with a bit more detail for the overdetermined problem, because in my experience, the overdetermined problem, the PD problem, is more difficult. The more you shift from geometry to analysis, the more difficult things become, in my opinion. So this also means that if you solve things in PDEs, then you can go back to geometry and help the geometers to solve something. So I hope that there are no geometers who get offended by my declaration, by my statement. Okay, so in order to understand whether there are non-symmetric domain for the overdetermined question, let's say, but you will see that the same result will hold for the constant mean curvature problem, then I want to use a variational formulation of the problem. What is the variational formulation of the overdetermined problem? So let me start mentioning this fact. You consider, so we are inside the cone, we consider any domain omega, and we consider this problem here. For the moment, this problem is not overdetermined. I'm just considering the Poisson equation with u equals 0 here, normal derivative equals 0 on the boundary of the cone. And I consider, and it's easy to see that there is a unique weak solution in the Sobolev space of the function, which are 0 only on the relative boundary. This is very easy, just because it's an easy equation. Then for I will call u omega this unique weak solution. So it depends on the domain omega. Then I consider the energy of this solution. The energy is given by the value of this functional in omega. So the usual Dirichlet energy minus this term, which comes from this term here. And so this functional is well known for people who study this problem. It's called the torsion energy functional. And it was usually defined for the Dirichlet problem in not in the setting of the cone, but this is exactly the analog of that. And in shape optimization theory is a famous problem called the Saint-Venant problem, the one to minimize this energy among all possible domains. So in my context, in my case of the cone, what I would like to do is to understand what are the minimizer of this energy functional among all possible domains omega which are inside the cone. Okay? So this is a classical minimization problem. It's very natural. You would like to understand for which domain you have the minimal energy, which is important in many applications. But let me first give you the relation with the overdetermined problem, because this is again a functional, as the perimeter was it before. This is a functional which depends on the domain. So it's the variable of this functional is the domain omega. So let me take the derivative of this functional with respect to variation of the domains which leave the volume fixed again. Then if I do this operation, which is an operation which is known in analysis and is called the domain derivative technique that you can do with some computation, you end up with this characterization that every critical point of this energy functional with the fixed volume is a domain omega for which you have a solution of the overdetermined problem, because if you have a critical point in this energy, then you have this extra condition that this function u omega has a normal derivative which is constant on the relative boundary. So this means that the domains I'm looking for, the one for which there is a solution of the overdetermined problem, are exactly the critical point of this functional. Okay, so now, then of course the result that I had with the Juriot-Rall in a sense characterized the critical points. Okay, so now I was telling you I would like to understand when in a non-convex cone I may have a solution of the overdetermined problem which are not the spherical sector. Okay, so then I take advantage of this variational formulation, and I will show you that there exists non-radial minimizer for this torsional energy. So I prove even more, not only that there exist non-radial critical points, but there exist non-radial minimizers. Okay, how do I prove this? Okay, before I describe this, I don't want to be too long, but what is the strategy? The strategy is a very simple one. I mean, it's what everybody would do in a courses of calculus or analysis. You take a function J, which is my energy functional, which depends on the domain omega, okay? I want to prove that, so first of all, if I take, let me denote by omega 0, the domain which is the spherical sector. Okay, for sure, this is a critical point of this functional. So the derivative is 0, always with the volume constraint that I will not add all the time. Why is a critical point? It's a critical point simply because of this characterization. Because of this characterization here, you see, the critical points are the ones for which the normal derivative is constant. And of course, the torsion function in the case of the spherical, since it's a radial function, the normal derivative is constant. So this is a critical point. I would like to find another critical point, actually a minimum, another minimum. So I want to prove that this is not a minimum. So how would you prove that something is, some critical point is not minimum? You study the second derivative. You study the second derivative at U0, which at omega 0, sorry, not U0, omega 0. So it's a domain, the second shape derivative, the second domain derivative. You study the second derivative. You can imagine that this will give you some kind of quadratic form. And you will prove that this quadratic form is not positive definite. So you have to find some direction on which this one is negative. So this is a way, usual way to prove that something is not a minimum, cannot be a minimum. It's not a local minimum, so it's not a global minimum. Okay? So, and this is what we did. I will tell you, this we refers to collaboration with Alessandro Jacopetti and Tobias Wett. Okay, so I want to prove that the second derivative at the trivial domain, which is a spherical domain, is not positive definite. But in order to prove this, I mean, you understand, but I will tell you that if you take the shape derivative, this is not an easy object. And if you take the second shape derivative, is even worse. So what we do, we restrict a bit the class of the sets we consider. Okay? So I consider the sets inside the cone, which are strictly star-shaped. Why do I consider strictly star-shaped domains? Because if we take a domain inside the cone, which is strictly star-shaped with respect to the vertex of the cone, then the relative boundary is the radial graph of a function defined on the domains on the sphere which spans the cone. So, and this helps me to write this functional J of omega as a functional of functions defined on the part of the sphere which spans the cone. So a strictly star-shaped domains is a domain whose relative boundary is a radial graph that I can parameterize in this way, where phi is a C2 function, small omega is the domain on the sphere which determines the cone, which spans the cone. Okay. So the domain omega phi is just the subgraph. The strictly star-shaped domain is the subgraph of with respect to the graph of phi. So in particular, with this parameterization, if I take phi equals 0, I get precisely the spherical sector. Okay, so anyway, so this is the spherical sector, and this is the star-shaped domain, and the gamma phi is the relative, the boundary is the radial graph. Okay, once you do this, I do this also because I have to fix the volume, but the volume for domains which are below a graph is very easy to write, it's just this formula. And so I consider the manifold of the function in C2, which fix the volume, because I have this constraint. And then, okay, then now I skip many details, but then I have to take the second derivative. So as I told you, I want to compute the second derivative in the spherical sector to prove that the quadratic form, you will see that this is a quadratic form, is negative definite in some direction. So when I take phi equals 0, so this means that my domain, the trivial graph is the spherical sector, I can write down, you have to do many computations, but it comes with a certain expression. Okay, don't worry about these things.
The last term should be B.
Should be?
B.
No.
What is that?
Is here? Is this? That's why I said I skip a bit. When you write, when you take these shape derivatives, it comes into play the derivative of your initial function with respect to the parameter which gives you the deformation of the domain. And this I will call U prime here. And so this U prime solves something, this enters in the second derivative. Okay, it's technical, but okay, so the theorem that we have, which was last year with Alessandro and Tobias Wett, is that the stability of the critical point or the trivial critical point depends on the Laplace-Beltrami operator on the sphere. Because what we could prove if you take the first non-trivial eigenvalue of the Laplace-Beltrami operator on the domain on the sphere which spans the cone, if this eigenvalue is smaller than n-1, then phi equals 0. Phi equals 0 means the spherical sector is not stable. So there is a direction, which is indeed the direction of the eigenfunction, corresponding eigenfunction, for which you have instability. And so this is a bit because, I mean, if you manage a bit this quadratic form, this is related to the quadratic form which defines the eigenvalues on the sphere. This is the reason why this comes into play. And instead, we would prove that if this is bigger than n-1, then phi equals 0 is a stable critical point. And actually, you can prove that the instability increases whenever this becomes smaller and smaller. Okay, obviously, if you take a convex cone, we know that the only minimizer are this one. So of course, for convex cone, you must be in this, and this was known in differential geometry. But anyway, if you like, this is another way of seeing that this eigenvalue is bigger than n-1 when you have a convex cone. Okay, so this is a result. So this tells you that there is a big class of non-convex cone for which the spherical sector are not local minimizer and so are not global minimizer. But I want to produce a global minimizer which is non-radial. So up to now,
Omega has a fix of the surface.
Omega, the small omega,
yeah.
Yes. Sorry, maybe this was not clear. So I have a cone, right?
Yeah.
So what is a cone? So I take the sphere, the unit sphere, and I have a certain domain, small omega, on the sphere, which spans the cone. So this, for every fixed cone, I have a fixed omega. So what I'm telling you is that if this small omega, which I have used to define the cone, is such that the first eigenvalue of the Laplace-Beltrami operator is less than n-1, then something which is apparently disjoint, but then the spherical sector is not a minimizer.
So the radius is 1. Right?
The radius is 1, exactly. Yeah, the radius is 1. In fact, you fix the measure as for the unit spherical sector. Okay.
Sorry.
Okay, so up to now, so this is nice. So first of all, let us produce an example of domains for which this holds. Okay, and these are two domains for which this holds. So if you take a neighborhood of the equator, or if you take this kind of dumbbell domains on the sphere, then it is true that the first eigenvalue is less than n-1. There are other examples, but they are not easy to find, at least for me. I mean, not expert in differential geometry. So, I mean, it's easy to see when you have the reverse inequality because every convex domain on the sphere satisfies this. But it's not easy to see. These are Neumann eigenvalues. Neumann eigenvalues do not have, for example, monotonicity property with respect to the shape of the domain. So it's not easy, but at least we could produce some example. Okay, so far we should be already very happy. But I'm not completely happy because I have not told you if a minimizer exists. Because I am in the unbounded cone. What I have proved so far is that the spherical sectors are not the minimizer of this torsional energy. Okay, but I would like to prove that there is a break of symmetry, that there exists a minimizer. Otherwise, okay, that are not minimized, but the minimizer may not exist at all. Maybe the least energy is achieved for domains which escape at infinity, for example. In fact, this is a non-compact problem because the conies are unbounded. So the question of the existence of the minimizer is not so easy to solve, because in principle, you could have a minimizing sequence which escapes to infinity. So now let me skip this because it is late. I'm just tell you that now that I want to show you that the minimizer exists, but so this is a typical problem in shape optimization theory. I want to prove that there exists the best shape, and as usual in calculus of variation methods, if you want to prove that a minimizer exists in a certain class, maybe you are not right. You have to enlarge the class, prove that a minimizer exists in a very large class, and then try to regularize it. And this is what we did here. We consider a class of quasi-open set, but okay, I don't want to tell you what they are. And I want just to tell you that we use the kind of concentration compactness argument in order to prove that for a minimizing sequence, it's not convenient to escape to infinity, but it stays in a bounded region and gives you really a minimizer. And people who are familiar with the concentration compactness principle of Lyons, maybe they know that in order to prove the existence of minimizer, you have to avoid a few situations, the vanishing, dichotomy, compactness, and so on. Okay, so anyway, what we could finally prove with Alessandro Jacopetti, Tobias West, is that indeed the condition for the existence of the minimizer is very, very good, very light. As soon as your domains omega on the sphere has a measure which is smaller than the one of the half sphere, then a minimizer exists. Mm-hmm. And then once it exists, you prove that it has certain properties, bounded, open, connected, and some regularities up to a certain dimension and so on. So then finally, if I put together these two conditions, this one which tells me that the minimizer cannot be the spherical sector, and this one which tells me that a minimizer exists. So if I put together these two conditions, then I get a non-radial domains for which the overdetermined problem has a solution. Okay, so we have achieved our break of symmetry result. And let me just conclude saying that exactly the same thing. Okay, so let me just mention this question. Of course, I don't know, unfortunately, the shape of this domain. I have some idea because I know what are the eigenvalues, the eigenfunction of the Laplace-Beltrami operator on the sphere. So I may imagine how an optimal shape should be, but we do not have yet any result on that. But let me just tell you that the same approach works for the isoperimetric problem, which is the geometric problem. So again, exactly with the same condition, we can prove that for the isoperimetric problem in the cone, a minimizer exists and is non-radial. And I didn't give you let's say, the explanation of this because this is easier than for the overdetermined problem. Because when you are in the class of a radial graph, it's very easy to write the perimeter of the radial graph, because I mean, it's a radial graph, so you know how to compute the n-1 dimensional out of measure. So to take the first and second variation as we did here, this is much easier. And you end up exactly with the same condition. So again, there is a very strong relation between this problem. So minimize break of symmetry holds for the constant mean curvature problem or for the isoperimetric problem, as well as for the overdetermined problem, exactly with the same condition. Though, I mean, they are in a parallel, obtained in a parallel way. And so, of course, this also implies that there is a constant mean curvature surfaces which intersect the cone orthogonally and is not a spherical cup. And again, it would be interesting to understand the shape of this non-radial constant mean curvature surfaces. Okay, thank you very much. Sorry if I have taken a bit more time.
Thank you very much for the nice talk. Are there any questions? I had a question because I wanted to look at the picture. How would one of these, like for example, in the case where you have these two poles connected by this narrow
The
edge.
dump bell domain.
Yes. So how would you expect this optimization, this surfaces to go?
Ah, okay.
So at least.
I have yeah. Okay. So this is your cone, okay? So the radial sector would be a cone whose relative boundary is all this, okay? So now I want to reduce the relative boundary, fixing the volume. So what I do, I lift a bit this, and I make this a bit below. Okay, so, and then I connect them with some surface. So this is my guess. My guess is that the surface which is better than the other one is a one where in one part of the dump bell, it goes a bit up, not so much, just a bit. And the other part, it goes below. So you see that the measure of these two parts changes.
Again, would be that they are not the same size. Both of these,
no, they are not the same size anymore.
They were the same
No.
size, then this would not.
Because this has a small radius, so this is different. But it's very tricky because you have to think that this cannot be part of spheres because they must have the same constant curvature. And if this was a sphere with a certain radius and this was a sphere with another radius, they do not have the same constant mean curvature. So why do I think this? Because if you take the eigenfunction corresponding to the first eigenvalue in this domain is 1 and -1 and almost 0 in the middle. And it goes from 1 to -1. So 1 means that you go a bit up, -1 you go a bit down. So this is my guess. So, and here there is a tunnel which goes like this. So, and when the tunnel in the middle gets shrinked, the eigenvalue gets smaller and smaller. So you end up almost with the two things like this. And then you understand that it's more convenient for the volume to be just one of this and just a small piece here. So because so there is more, but what is really puzzling about this and also about, let's say, this kind of picture that I have in mind is that they have to have constant mean curvature. So you cannot just do this just taking the spheres, and they have to intersect orthogonally the cone. And this is also not true in general, no, because so if it's a piece of a sphere, it intersects orthogonally, but then they cannot have the same constant curvature. So I don't know. I think it's very tricky. It will be very nice to have an idea, I mean, more precise idea than what I have. I mean, just some kind of, let's say, proof that you go into this direction. One should use the eigenfunction to prove that the direction instability modifies the surface in this way. But this is not so obvious. There is a bifurcation. There's a kind of bifurcation in a certain sense, because when you have a λ1 precisely equal to n-1, we are in the border between spherical symmetry and not spherical symmetry. So I don't know.
For the equal case,
No, but it's not only even in fact, let me mention another beautiful open problem. If you take λ1 bigger, λ1 of the Laplace-Beltrami operator on the sphere bigger than n-1, I know that the spherical sector is a local minimizer, but I don't know that it's a global minimizer. If it is convex, yes, because we have the results. But this condition is lighter than the convexity. If it's convex, satisfies this condition. So this could be the right, division between having the isoperimetric inequality or not.
And a really naive question: can you put this on a computer?
Yeah, I would give you $1 million. Can do that. I don't. I mean, I'm very poor in these things. If somebody can do it, this would be very nice. Yeah, even approximate answer would be very nice, because it would make us to understand what kind of surface, because it must be constant, the curvature. So it's not cannot be a piece of a sphere. But if you think about other constant mean curvature, for example, like cylindrical stuff, how can they intersect the cone orthogonally? I mean, these are not. And also, I believe that at least when the eigenvalue is close to this number, it must be close to the spherical factor. But a small modification which allows you to reduce the perimeter, fixing the volume. So Figalli and Bayer, they proved it that you can perturb the convexity a bit, and you still have the isoperimetric inequality, but they could not give a quantitative perturbation. I believe that the perturbation is in terms of this eigenvalue, but that is not up to now. It's not solved.
Are there any other questions? So if not, let's thank the speaker again. We invite you all to a cocktail that is in the common room, coffee room, the room.
Can I move this? I don't know your name.
I work in another.
Okay, that doesn't matter.